Hey guys, just wanted to have a couple practice problems for lesson 5 and lesson 6. Please remember this is not everything. Make sure you review the stuff we've done in your packet. But go ahead and whenever I ask a question, go ahead and pause the video and see if you can answer it on your own, and then unpause the video and then or play the video, and you can watch what I do for good practice. The first problems that we did in lesson 5, we talked a lot about situations that would produce quadratic functions, or if you graph them, would form parabolas. And one of those situations was if you throw a rock off a cliff or throw something in the air, it's going to be a quadratic function. The time versus distance is going to be quadratic. So here's a situation. You have a rock thrown off the cliff with an initial velocity. So as you're throwing it, it's 20 meters per second. The constant of acceleration is 32 meters per second. And remember, what that means is every second, the speed is going to increase another 32. Make a table of time versus distance. So see if you can do that. So what you should have done is you have the time, or the x, and I'm going to do a couple of them. Do 0 seconds, 1 second, 2, 3, and 4. You could keep going, but you'll get the idea after you do a couple of them. Then you're going to have your speed, which another way that we can write speed is your rate. And we could think of the rate as being, in this case right now, since these two are going to be related, we could think of the y, this as being your y coordinate right now, or your y variable, because this is a function of your time. The more time it goes, the faster it's going to go. So we know at time of 0, it's going 20, and I'm not going to label it, but this whole chart is going to be in meters per second, because it's speed. After 1 second, we're going to use the 32, and it's increasing 32. So now it is at 52 meters per second. Plus another 32 would be 84. Plus another 32 would be 106. No, I'm sorry, 116. Plus another 32 would be 148. So now we talked about that in order to eventually get the distance, which we'll put over here, distance is equal to rate times time. But you can't actually multiply using this rate because at 1 second, the rock hasn't been actually going 52 meters per second the entire time. So what we need is we need to make a column of average rate. And this is really the rate that we're going to use. Now to find average, well, the first one's easy because if all you've been going is 20 miles per hour, your average rate is 20. But to get each average rate, you take the rate that you're going at the end of 1 second, and you're going to add it. You're going to average it out with what you started with. So we started at 20. We're at 52 meters per second. And remember, average rate is also in meters per second. So 20 plus 52 is 72. Divided by 2 is going to be 36. Here, 84 plus 20 is 104. Divided by 2 is 52. 116 plus 20 is 132. And 132 divided by 2 is going to be 66. And here, 148 plus 20 is 168. And 168 divided by 2 is 84. So now that we have our average rate, we could almost cross these off. We don't need these anymore. Because to find the distance, we're going to take, and actually, by the way, before we move on to distance, you should notice that the relationship between x and your speed, or your time and your speed, is actually linear, because you should see that it's going plus 16, plus 16, plus 16. So that we have a little bit of an issue here, because instead of going plus 16 and plus 16, this one goes plus 14. So I must have made a mistake somewhere. So let's go back and see if we can figure out where our mistake is. So I added 32 here and got 84. And 84 plus another 32, sure enough, equals 116. So this is 116. So I must have made a mistake in finding my average rate. 116 plus 20 is 136. And 136, you can see I put 132. 136 divided by 2 is 68, not 66. Because I knew that it was supposed to be linear. Now it goes plus 16, and then again, plus 16, except it looks like I made another mistake. I'm sorry, 68. So yes, it does go plus 16. That's a 68 right there. So now to find our distance, all we have to do is do our time times our speed. And I know that this is all in meters, measured in meters, 20 meters. 1 times 36, 36. 2 times 52, 104 meters. 3 times 68, okay, is 204. And 84 times 4, 4 times 84, is 336. Now, if you notice right here, the difference between 20 and 36 is 16. The difference between 36 and 104 is actually 104 minus 36 is 68. The difference between 104 and 204 is 100. And the difference between 204 and 336 is 132. What you're going to notice is while these aren't common differences, the difference of the differences for each of these is going to be 32. Except I made a little mistake here. From 20 to 36 is 16. From 36 to 104 is 68. That's right. So 16 to 68. Oh, sorry. Is 52. So it looks like we made ourselves another little mistake. So let's see if we can figure out what we did. Oh, I'm sorry. I said that 0 times 20 is 20. It's actually a distance of 0. So now we have all of 36 to 68 would be another 32. So now you can see that the difference of the differences is the same. So the relationship between time and distance we know is quadratic. So on to the next one. Write an equation that relates speed as a function of time. Okay? And then before you do that, you could do this one too. Write an equation that relates distance as a function of time. So I'm going to go over here to this. We're going to go back a little bit. And I'm going to go ahead and remember I said that speed and time is linear. So to find the equation between the two of them, I first have to find the slope. So it's going plus 16 every time. So that's the slope. So we write linear equations in slope-intercept form, or we can write them in slope-intercept form. So 16x, and then what's the y-intercept? Well, when x is 0, y is 20. So the relationship between time and speed is 16x plus 20. Or I can, if I wanted to, I can say that the rate equals 16 times the time plus 20. If you gave me the time, I could put it in here and find out the speed. If you gave me the speed, I can solve for t and find out the time. Well, now that we know that rate equals 16t plus 20, it's going to help us find this function, 16t plus 20. Remember, distance equals rate times time. But if you're going to graph it, we want to have only two variables. So instead of rate, we know that another name for rate is 16t plus 20. So I could plug that in for the rate and keep t as the variable t. And then when you multiply this out, you get your quadratic function, which is 16t squared plus 20t. This would be the same exact equation that you would have gotten if you took these as your L1s in your calculator and these as your L2s and found the quad reg, or the quadratic function that would meet x to this y. When does the rock travel 1,000 feet? So basically, the way I'm going to do that is I'm going to put my quadratic equation into my calculator. Clear that out of there. So remember, it was y equals, oh, I actually forgot it already. 16t squared plus 20t. 16x squared plus 20t, or 20x. And then if I go right to my table, I can see all the situation. Now I want to go back to 0, so I'm going to have my table. I'm going to go back to my, see it says right here, table set, second table set. I don't want my table starting at 30. I'm going to have it start at 0. Now I'm going to go back to my table. And the question was, when does the rock travel 1,000 feet? So I'm going to look for when my y, remember my y was my distance, right between 7 and 8 seconds, I can see it crosses the threshold of 1,000 feet. The next question says, when is the rock after 10 seconds? You could do this two ways. You can go down to x of 10, and you could say the rock is at 1,800 feet, or traveled 1,800, I'm sorry, it's meters. Or another thing you could have done is just plugged in, instead of 16t squared, now we know that t is 10. And I think it was 20 times t. Well, the t is, again, 10. If you solve this out, you will indeed get what we got over here, which is 1,800, which is 1,800 feet. Okay, we're almost done. What if you wanted the equation that relates height of the rock? So instead of distance, we want the height of the actual rock as a function of time, and the cliff is 10,000 meters high. How would you do that one? Okay. Well, what you should have remembered is to find out how far the actual rock travels. How far it travels down is represented by 16t squared plus 20t. Well, if you start at 10,000 feet, to find out where the rock is, we would just do 10,000 minus, and then I got to put this whole thing in parentheses. Can't forget the parentheses, because you're going to end up simplifying this by distributing the negative sign, and you get 10,000 minus 16t squared minus 20t. Oh. And I'm just going to turn this around so it's in standard form. Negative 16t squared minus 20t plus 10,000. And this would be the equation we can use to find out. If you tell me that it's been 5 seconds, and I plug in a 5 into that t and that t, you'll find out the exact, it's not distance anymore, the height of where the rock is. So the last question is, when does that rock hit the ground? Well, we're going to plug in our new equation into y equals. So remember, it was negative 16x squared minus 20x, and then it was plus, just make sure I got it right, plus 10,000. Remember, when the rock hits the ground, would be the height of the rock would be 0. So I can look on my table, and I can see that my rock, as the seconds go, it's going downward, it's still in the, up, right here. So at 24 seconds, it was at 304 feet. At 25 seconds, it went, negative would mean it went underground. So you would say somewhere between 24 and 25 seconds, it hit the ground. Okay. This is something we did in class, so I'm not going to talk too much about this, but just a couple key points. This is from lesson 6. Who is faster over the interval? So faster, remember, this is when you'd have distance and not speed, and you have time over here. So when you want to know who's faster, what you're looking for is over the 6 to 8. So 1, 2, 3, 4, 5, 6. So from here, 7, 8, to here. Now, this isn't going to really work out for the blue, which is an exponential, because I'd have to go up farther to find it. But to find out the speed of the red, remember, you're taking the distance that you are here. You're subtracting the, well, actually, you're taking the distance you are here, because it's going to be bigger, subtracting the distance here. So that would give you the total distance, and you're dividing it by the time. Well, in this case, if you go from 6 to 8 seconds, 2 seconds have passed. So distance divided by distance would get you the total distance you traveled from here to here, which would be represented from whatever, this represents. And then you're dividing it there, and that's going to get you your speed. Because remember, while distance equals rate times time, if you turn this around, rate equals distance divided by time. So we want to take the distance that we traveled divided by time. The other thing that I wanted to point out, that someone asked a really good question in class and said that if you can't see the rest of the graph, how do you know which one of these is an exponential, and how do you know which one of these is a quadratic? Remembering that in an exponential, you are taking like the number 2 to the x power. In a quadratic, you're taking x and doing it by the same power every time. So if you think about it, an exponential eventually is going to be steeper than a quadratic. Because, for example, say that x is 4. Well, if you put a 4 in for there, you get 81. If you put a 4 in for there in the quadratic, you only get 16. So you can see that, by putting bigger numbers as the exponent, eventually it's going to be a lot, I hate to use the word steeper because it's not really a slope, but it's going to increase at a much faster rate than a quadratic will.